Chapter 8 is chock full of right triangles, and then introduces you to trigonometry. But we ease into all of this with something most of you have probably already seen and worked with before, the Pythagorean Theorem. If a triangle is a right triangle, then the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. I have to say, this description is quite a mouthful for a simple concept. That sum of the squares of the lengths of the legs part is ridiculously brutal. Your English teacher would probably ding you if you put that into one of your stories. In any case, it is important that we start out with a right triangle. Without that right angle, this doesn't work. Now, the official theorem doesn't actually name the sides. It calls them legs and hypotenuse, but most of you are probably used to seeing the sides like this. With that done, we can boil down this theorem to a squared plus b squared equals c squared. That is probably nice and familiar for you. And a squared plus b squared equals c squared is certainly a lot cleaner, simpler, and clearer than that theorem description. That is great and all, but there is one thing to be wary of. What happens if someone is a bit evil and does this? This means that our equation turns into this. It is technically still correct. The theorem just mentions legs and hypotenuse, and those are still the legs and hypotenuse. But technically correct or not, it is still confusing, and intentionally so. And there are some teachers that just love to do it to you to keep you on your toes. Just realize that technically this is fine. It is still the Pythagorean theorem. But for practicality's sake, if you remember the Pythagorean theorem as a squared plus b squared equals c squared, that is usually just fine. Since this is likely the most famous of geometric theorems, it makes sense to give a little historical perspective. The theorem is named after a man named Pythagoras, who was born somewhere around 572 to 569 BCE on the Greek island of Samos. I'm still not used to that BCE thing, instead of just BC. Pythagoras was more than a mathematician. He and his followers made a lot of discoveries in music, astronomy, and medicine too. Pythagoras was a major philosopher who founded a quasi-religion named, appropriately enough, Pythagoreanism. Since we are giving you a little background on this theorem, it is important to note that Pythagoras didn't even come up with this idea. The concept was not new in Pythagoras' time. There is evidence of the Egyptians, Babylonians, Indians, Chinese, and possibly even the Mayans all knowing and using the concept. The Babylonians actually have some pretty sophisticated work on the topic on 4 clay tablets that have been found from some 3,750 years ago. It is interesting that we call this thing the Pythagorean theorem, even though he didn't come up with the idea. However, we do know that Pythagoras proved it, showed it, and taught his followers, and then his followers disseminated the idea orally, giving Pythagoras the credit for it. And that's how we call it the Pythagorean theorem today. Enough of the history lesson, though. Back to math. A Pythagorean triple is a set of positive integers, a, b, and c, that satisfy the equation a squared plus b squared equals c squared. The book actually says non-zero instead of positive, but I don't think that's quite right. Negative numbers, although they do satisfy the equation, shouldn't be included. Not that it's a big deal one way or the other. The basic idea is a Pythagorean triple is a set of 3 integers that work in the Pythagorean theorem, like 3, 4, 5, or 5, 12, 13, or 8, 15, 17, or 7, 24, 25. You can do a quick check yourself that any of those sets does, in fact, successfully work in the Pythagorean theorem. In addition, any multiples of these numbers also work. For example, you can take the 3, 4, 5 Pythagorean triple and multiply it by 2 to get 6, 8, 10, and that is also a Pythagorean triple. Or multiply it by 3 instead and end up with 9, 12, and 15, which is also a Pythagorean triple. That works for any Pythagorean triple that you have, and you will begin to see the same Pythagorean triples over and over again, since math teachers don't want to create problems with gigantic numbers, thus they stick with a few Pythagorean triples that are the lowest values. So most of you have probably done the Pythagorean theorem. But how many of you have actually done the converse? Most of you have probably never even heard of it. This was the Pythagorean theorem. It's a nice and simple if-then statement. If-then statements have converses, and I'm sure you remember those. The converse flips it around, so let's do that, while cleaning up a few language pieces. The converse of the Pythagorean theorem says that if the sum of the squares of the lengths of the 2 sides of a triangle equal to the square of the length of the 3rd side of the triangle, then the triangle is a right triangle. Phew! Once again, that's quite a mouthful. Here's what makes more sense to students. That's the basic idea. If you like the full-on definitions better, fine, go with those. But this is the idea boiled down to what most students like better. The converse of the Pythagorean theorem lets us figure out whether 3 lengths make a right triangle. The basic premise is, if you have a triangle, try and calculate a squared plus b squared equals c squared. And then if you find that it does work out, then what you have determined is that the longest side c is exactly the right size to make a right triangle. This definitely lets us find right triangles, but we can actually take this idea and tweak it a bit to get 2 corollaries which let us identify obtuse and acute triangles also. The basic question to ask yourself is, what happens if the longest side c is no longer exactly the right size to make a right triangle? Look at this triangle here, a nice perfect right triangle. What would happen to this triangle if I made c a little longer? It would no longer be a right triangle. What would it be? By making c longer, I have transformed the triangle into an obtuse triangle. Now c is too large to make a right triangle, so my formula changes to this. In obtuse triangles, c squared is too large compared to a squared plus b squared. But let's go the other direction. What if I make c a little smaller? What happens then? Now it transforms into an acute triangle. C is no longer the perfect size to make a right triangle. Now it is too short, so my formula changes too. In acute triangles, c squared is too small compared to a squared plus b squared. Now a quick summary. We have determined that when c squared is the perfect size, we end up with a right triangle. And when c squared is too big, we end up with an obtuse triangle. And when c squared is too small, we end up with an acute triangle. That's great. With the way I have been saying all of that, it should be obvious that c squared is the key to everything. C squared is what you should focus on. There is a common error students make. Let's say a student remembers c squared is the key. They also remember the animation of c squared getting bigger and making an obtuse triangle. Thus, if c squared is too big, then we have an obtuse triangle. All of that is perfectly correct. That is absolutely what they have to remember. Given that logic, the student should be using this formula. This is the one that says c squared is too big. But here's the problem. We have been saying bigger. C squared is too big. But there's this symbol, the less than sign, which doesn't say bigger to them, even though it is pointed in the right direction here. So I can't tell you how many students will flip that around to a greater than symbol because obtuse is supposed to be bigger. And now they are using the wrong formula. Does this sound like something you would do? I can tell you that I see it all the time. If so, if this is something you might do, then maybe it would help to rewrite the summary like this. Now the greater than symbol goes with c squared being bigger. Will that help? It's up to you. C squared is the key. So in practice, this is what happens with problems like this. A very typical problem might say, if three lengths of a triangle are 8, 18, and 15, does that form a right, acute, or obtuse triangle? Here are the steps that you should follow. Step 1. Square all of the numbers given. Remember we were dealing with a squared, b squared, and c squared, so we need the squares. In this instance, squaring all of our numbers results in 64, 324, and 225. Step 2. Identify which one is largest. This may be a shock, but the largest number won't always be third. If you need help with identifying the largest number out of 3, well, wow. In any case, that largest number becomes your c squared, and the key to the whole problem. The other two numbers are a squared and b squared. It doesn't matter which is which. In this problem here, that means 324 becomes our c squared, 64 and 225 are a squared and b squared. Our final step is to check c squared compared to a squared plus b squared. Your problem will fall into one of those three categories. In the example I have going here, since 64 plus 225 is 289, we need to compare 324 and 289. Hopefully that's not too difficult. Since 324 is too big, then our triangle is obtuse. It's always the same three-step process for all these type problems.